this was the paper published in ICLR 2024, Graph Neural Network for Learning Equivariant Representation of Neural Networks. So the main problem statement of this paper is this first line, like how we can design a neural network that themselves take a neural network as a parameter. So basically, what we are trying to do here is we have a neural network, right? Let's say any neural network. This also work for CNN also. So we design another neural network that predict the behavior of this first neural network. For example, if we pass the parameters of this second neural network, then the first neural network can tell us about the what should be the weight initialization of this neural network. Like, how would be the result of this another neural network? So basically, we can generate neural network weights from their architecture. So they proposed a new neural graph architecture, basically, in which they represent the neural network as a graph, as a computation graph. So, okay. So basically, till now we have seen a lot of architecture which do this same task, but they have a lot of problems. Like they've mentioned, as we know that in a neural network we can permute the neurons in a layer. So basically, if we permute the neurons in a neural network, the other architecture doesn't support this permutation symmetry or permutation equivariance, I should say. So, so the problem is solved by representing a neural network as a computation graph or a neural graph. And they've also proposed invariance neuron symmetry, prop feature, which we'll discuss, and then graph transformer as a neural graph as an input. So this was their original proposition. So basically, as we know, this is the standard equation of a neural network. So sigma, or a non-activation function, bias plus summation of weight and output from the previous layer. So they have taken each neuron as a node of a graph, and they have taken the directed acyclic graph like that. So this is the dimension that I've mentioned. Like, the dimension of the weight matrix will be this. This is the first layer, this is the second layer, and so on. And the bias matrix is this. So they have defined the bias as a feature of a node and the weight as a feature of an edge, and they use the classic GNN algorithms to process this information. So as I said, neuron node is the basically neuron eye, and the node feature is the bias, and edge is the connection between them, and weight is the feature of an edge. So this is their edge representation, and this is this is the node representation, and this is the edge representation. And this is the diagram, like for layer L minus 1, any arbitrary layer, the weights are the edge features and node feature is bias. So so their approach is pretty simple, and it and we'll see the result of their approach as compared to the other existing approaches. So as of now, we have seen the MLP as a graph, and like I have defined this, the dimension of edges is n cross n into DE, and DE here it denotes the number of nodes and the edge features. Okay, and n is the total number of nodes in the MLP, and it will be the node of a graph. Okay. So now we have seen the MLP as a graph, and here So here they've also pointed out that denote node feature in the V are the set 0. One more thing I should point out, in the neurons, like in a random MLP, I can switch these two neurons, like I can shift these neurons, but I cannot change the input layer and I cannot change the output layer. Like, it is fixed. If we change this, then the formula or the working of the main functionality of neural network is also get changed, and they also handled this. Like, hidden layer we can do anything, but input and output layer, like, we cannot do. So they've solved this also, like how basically they've also used the node embeddings for the input layer and the output layer special, like to they've mentioned in their like the appendix section in the last. Okay, so now we will see a CNN as a graph. So there are a lot of things happening in the CNN architecture, and it is quite complicated to represent the CNN as a graph. Okay, so yeah, so in the CNN, basically, what are they? They have taken node as a like here I have described in the CNN. Okay, yeah, I'll come to this diagram later. Yeah, so in a CNN, basically the channel they've taken as a node, and basically channel means, by channel I mean the single channel of a multi-channel slice of the feature map, and they've taken this that means the flattened kernel as a edge feature. So what they did with the kernel, they defined this as the W max, basically the width and height, the maximum height and width, which is a classical hyperparameter in their classical hyperparameter search, and they zero pad all this kernel, and after zero padded they flattened this kernel. So representation of a convolution kernel is like this, as they have also printed that we zero pad the predetermined maximum kernel size in this example and flattened it. And after, like for example, we have an L number of layer in a convolution in a CNN, and this will be the dimension of the weight matrix, the filter basically, the filter where L belongs to the number of layer, L is the number of layer, Lth layer, and the B is the bias. Bias is same as the node feature. There's no change in the bias. Yeah, so there is no change in the bias as such. And yeah, this diagram I'll explain. Basically, yeah. So basically, permuting the filter in a layer while simultaneously permuting the channel of each filter in the subsequent layer effectively cancels out. So what that means is, in this diagram, if they change this or permute this filter, then this output will also get permute, and if this output get permute, then each filter in this next layer, in next kernel layers or next filter, will get permuted, but the output remain the same. So basically it is the property of their design, like how they have implemented is this is happening, like it is not changing the output if we, even if we change the filter. So this again I read this line: permuting the filter in a layer while simultaneously permuting the channel in each filter is subsequent layer effectively cancel out the permutation as shown in this figure. Okay, so now we have seen the basic representation of the MLP as a graph as well as the CNN as a graph, and here they've given the example. They've explained this further in the appendix, but they've explained this thing in the appendix, like how they've changed the kernel and how they've managed it. So now we, as we know, there are a lot of things going in the CNN. The MLP is pretty simple, but how they have mapped the CNN is the crucial part of this paper, because other researchers have not been not are successful in doing this, especially if we have a flattening layer, we have a convolution layer, we have a linear layers, and in further they have mentioned how they've taken nonlinearity like activation functions, ReLU, sigmoid, etc., and also they've implemented the residual connection. Basically they have given us the way to implement the residual connections. Okay, so I'll explain this, and then yeah, so they have also proposed this probe feature and how they have implemented normalization, and yeah, as direction, as I've said, they've used the directed cyclic graph. So okay, let's start from here. Yes, Subhanshu. Yes, I would like to ask you a question. Okay. So when you are explaining the CNN as a graph, okay, how
like how it is how it is said that um, every channel, or you can say every single slice of a three-dimensional channel input is considered to be a node.
Yeah.
No. Like it's not exactly clear to me how it is done. Can you reassess or re-explain the section where the CNN is considered as a node?
Okay. So yeah, CNN as a graph. Okay. So basically, convolution layer takes the input, like in convolution, in specifically, like this is the standard convolution, right? So convolution layer take the input of a multi-channel input image, like RGB or this. So C is the number of channel, and they've taken this. This channel is very important. Okay, we'll see how the channel play the role as a node of the graph. So we have basically the channel, and we have the kernel. So in a classical convolution CNN, we have a filter bank, basically where we stack all these kernel, all these multi-channel feature maps, and processes at a filter bank, collection of convolution kernels, as I said. So yeah, so these are the filters. This is like input height, width, and C. Okay, so they have taken, yeah. So here, so they have taken node as a single channel slice of a multi-channel feature map. Basically, this is a node, this single channel in a in this filter map. This is a node 1, let's say, this is a node 2, and so on. So in this way they have taken the nodes of the graph. Okay, so
Thank
here
you so
it was
much.
written the single channel slice of a multi channel feature map, or a single channel slice of an input corresponding to node in our neural graph. So, and the edge is pretty simple. The This is an edge, the edge feature. I mean, the connection are the standard convolution, like the how the connection are done in the CNN, and the features are very important. Like feature of the node is again the bias, and they've taken this kernel and zero pad this to a maximum width and height. This is a hyperparameter in their hyperparameter search in the mention in the appendix, and then they, after zero padding, they flattened it, and they use this this as a edge.
So they have used the flattened kernel features as the edge features, right?
Yeah.
Okay. Got it. Got it.
Okay. So because in MLP we have direct weight, as we have seen, this was their edge matrix. Like they have directly used the weights, and these are the node features, the bias.
Yeah. Yeah. Exactly.
Okay, so there are a lot of things going on in the CNN, especially we have the convolution layer, we have the flattening layer, we have the linear layer. They also mentioned residual connection, how to handle these things, and so let's start. So yeah, they've treated bias as the same way as in MLP, as I said, the node features. The kernel, however, do not treat identically due to their spatial dimension, which exists for MLP weights. To resolve this, we have they have flattened their special. Just a second. Yeah. Yeah. So kernel, by flattening their spatial dimension to a vector to ensure the spatial self consistency across the kernel of different size, we zero pad all the kernels to the maximum size and then flatten them. This okay. So maximum kernel size is chosen as a hyperparameter, and this was the initial the dimensions where the DE is again same as MLP, as they've defined here, like I've pointed out. So DE is same as this, denote the number of nodes and edge features. Okay, so now flattening layer, how they've used the flattening layer, there are two ways. First, they can use the MLP, because flattening layer is nothing but a neural network, right? So there are two ways to handle these flattening layers. The first way is the MLP. But if they do this, they have different representation for the CNN architecture and the MLP. Although the architecture in theory is the same, right? Let's say we have a unit. UNet have some convolution layer and then have some flattened layer. So if they have a different representation for the convolution layer and they have different representation for the MLP or a flattening layer, then their architecture became different. So they have taken two ways and conduct experiment in both the ways. Like first one is the yeah. So yeah, it is in the appendix section. So there are two mechanisms to address this traditional flattening, which we discuss in the appendix. So I'll discuss it later. Yeah, and then the linear layer. Yeah, the linear layer I was talking about, to treat the linear layer as a CNN and extract in the same fashion as an MLP. The downside of this approach is the convolution layer have a separate representation. And the yeah, so another way is to treat linear layer as a 1 cross 1 convolution. We also call 1 cross 1 convolution as the fast convolution, but yeah, so this is the second way to treat a flat linear layer as a 1 cross 1 convolution. Okay, so now we'll see how they model the heterogeneous architectures. So non-linearity. Non-linearity are the function applied like the sigma, like the non-linearity or sigma we call it. So they've create this as a embedding of the common activation function and add this as a node feature. Residual connection is implementing is pretty straightforward. Like if this is a neural network, then they just connect the direct edge from this input layer, say, to an output layer. And representation is also very simple. So residual connection are the integral component of the modern CNN, and residual connection directly connect this output, say, y equal to fx plus x to this. Incorporating this is pretty straightforward, and they just included the edge. Now let's see the node and edge representation. Though we like they mainly talked about the weights and bias, but there can be other features as well to the node and as well as the edges. For example, the gradients to optimize the setting. Basically, they have also described the way to optimize the neural network or to optimize the convergence. Like how do they find how to converge this neural network based on this their architecture. So yeah, so edge direction, as I have already pointed out, they have uses the directed cyclic graph or yeah. So it is for the forward pass. If they needed the backward pass, let's say for to compute the weights, so then they have added this E plus E transpose, like the extra feature representing the undirected features. So basically, it is still an directed acyclic graph, but they have used this E transpose as an additional feature. Yeah, so probe feature is their new thing. Probe feature, basically the concept of the probe feature is to give node and extra features. For example, we give the graph, we give the GNN a similar ability. What ability? Like as we human tend to interpret a complicated function by probing the function with a few input. Let's say we have a function. We try to see we give some inputs to this function and inspect the output. Let's say we have x square, so we will calculate, let's say 10 for 10 square will calculate 100. So basically they give the GNN similar ability and add the extra node features. And in the appendix they have mentioned the comparable result, like without the pro feature and with. So it is pretty useful technique. It is pretty useful. So basically they've just given the extra node features, right? Yeah, so this was their example. Let's say we have an fx of the layer 2 alpha, and this one is the formula for the layer 1 plus bias of layer 2. So they given the probe feature as like x comma alpha, and then they've given this the original, the main, the whole function, the output of the whole function. Okay, so yeah, oh, and also probe feature are invariant to all the augmentation on the input, because they've given everything like in their as a node feature. So it is augmentation of the input neural network parameter as long as it maintain the exact same function for the output of the hidden layer. Yeah, the function should remain the same. Normalization. Again, there are a few recent studies on this, and
I would like to ask one thing.
Yeah.
So when we are perturbing the inputs, like we are adding probe functions and etc. So I think it is taken care of for the dimension of every input and the output, like we get from the traditional CNN or any GNN.
Yeah, probe feature are just
like
the
how it is automatically being taken care of.
No, probe feature are just the node feature, node embeddings. They've added this for the whole layer. Like, I didn't get your question. Like, if we have, say, this MLP, we already have the embeddings for this node, embeddings for this node, and all. We can add this extra embedding to all these nodes. They just add this extra feature as a node embedding.
Okay, so we are adding to each and every node in the graph,
Yeah,
right?
yeah, yeah, yeah. Like for
Okay,
each
got
layer,
it.
for one layer, like for this layer only,
Okay.
not for like every layer.
Got it. The thing is,
And then they've also implemented the normalization, like batch norm or adaptive normalization. There are normalization in the MLP or CNN. So basically, mean, standard deviation separately for the neuron. This operation, however, yeah. So applying the normalization to just a neuron will break the symmetry. So what they again did is they applied this for the whole across the whole layer. So we compute the single mean and standard deviation for each layer. So yeah, again this same thing. They computed the mean and the normalization basically for each layer, and then they applied. And similarly for the bias, as we can see these equation, they normalize the weight, and then they normalize the bias for the whole layer. So in this way, the permutation equivariance is still maintained. Then the positional embedding. Yeah, the positional embedding is pretty important, as I initially introduced with this thing. So before processing the neural graph, we augment each node with a learned positional embedding to maintain the permutation symmetry of the hidden layer. The nodes corresponding to the same intermediate layer share the same positional embedding. That means the node of the same layer will have the same positional embedding across the layer. So again, it still maintain the equivariance because they have used this positional embedding same across the layer. Why this positional embedding is important? The reason is that we cannot permute the input and the output layer of an MLP. We can permute the hidden layer, but we cannot permute the input and output layer. So to handle this, they have used the positional embedding. Although in as we are discussing GNNs, it automatically have a special ordering because it uses the adjacency matrix and all, and the algorithm, classic algorithm GNNs. So so using positional embedding allow immediate identification, eliminating the need of multiple local message passing steps. However, we we distinguish between the symmetries of input and output node and those of hidden nodes. In a neural network, rearranging the input node generally alters the network underlying function. In contrast, the graph representation is indifferent. And to address this discrepancy, we introduce the unique positional embedding for each input and output layer. Hidden layer also have positional embedding, but it is but for this issue, like which issue they are talking about, like we cannot permute the hidden, we cannot permute the input and output layer nodes. Okay, so now we have seen their models for MLP as well as the CNN. Now let's see the learning with the neural graphs. Yeah, so it is their name of the architecture, neural graph. So yeah, GNN. Various GNN variants exist. They have uses the PNA because of this reason. What reason? Because they also do updation of the edge features. Like here they mention edge features and hidden layer. So they've used the PNA because not all the GNN algorithm use the edge feature and update the edge feature in the hidden layer. In the GNN.
Can you
Yeah, hello.
explain what is a PNN?
Yeah, PNA. No, I didn't get it. Your voice is cracking. Hello, your mic is off. Okay.
Asking like, what asking like, can you explain is PNN because I'm not aware of it. Basic document
Okay.
can start our
Okay. Okay. So we'll see this PNA architecture later because I didn't go through the exact detail of this algorithm. But the main portion is simple. Like they in this, not all the GNN algorithm update the edge feature. So there are a very few algorithm of the GNN or networks which use the edge feature and update this also. So it is one of them, and okay, we'll see definitely. But yeah, so this is their updation of the embedding, like the k+1 is equal to 5, and then they use the edge feature, the VJK and VIK. Like this is the basically they have also considered the self loop, just to from it is clear from there, because they have used I as well as J of the kth layer as well as the embeddings to updation. Okay, so yeah, this is their message. And then yeah, this one is very important for this perspective. So transformer should also be, they basically they combined every art, they try to they try to form their architecture which can handle multiple architecture like CNN, MLPs as well as the transformers. So although their transformer section is pretty weak because the transformer portion and formulation is not good. They've mentioned that in the limitation section also. Like yeah, so yeah, if efficiently representing the transformer as a neural graph remains a challenging endeavor for this research. So it is their main limitation. Yeah, so basically for the transformer, similar to GNN, the original transformer encode the common variant and do not accommodate the edge feature. We use the transformer variant with the relational attention. So basically, they've uses the modified architecture of transformer from this, mainly because of this reason, because they cannot account for the edge features. Yeah, so their experiment was done on two parts mainly, the INR classification and style editing, and another is for the prediction of the CNN generalized from the framework. For CNN, they've used this MNIST or MNIST dataset, or like the weights and bias of each neuron. It's a pretty big dataset. Okay. So yeah, so for INR classification, they've summarized the importance of the positional embedding and everything in this next table. So let's quickly see this. So it is accuracy and number of probe feature. Accuracy versus let's say number of probe feature, and they have a lot of different architecture going on. So NGT is basically neural graph transformer, where GNN is the neural graph neural network. So basically, this is for the transformer and this is for the GNN. Yeah, so their setup is pretty simple. The single INR for the image MNIST, and the second contain the INR per image of the fashion MNIST. Yeah, the result are pretty much the same. Like you can see from this table, there are not a lot of research which do this kind of task, but yeah, their NGT definitely dominates these parameters. Another is for the CNN. Like I'm not going through a lot of detail of the results, mainly because the results are pretty much summarized in this table. For example, these are the another other architecture which also perform the task on this dataset, basically to optimize the weights and bias and activation for these datasets, and their transformer architecture works the best. Like in this case, GNN also is good. Yeah, so learning to optimize is there another task. Basically, learning to optimize, what they do is,
I would like to ask one thing.
Yeah.
So they have said that getting transformer as an input to the GNN or to the neural graph is a challenging endeavor, but it seems like from the results from the table, like it outperforms the GNN approach.
Yeah. So basically, what happened is they use the modified version of the transformers, as mentioned from this paper, to accommodate the edge features. They are not using the classical transformer. They've used the variant of it. We use the transformer variant with the relational attention to address these edge features. So Based on that, they mentioned result. They cannot accommodate the result from the classical transformer model proposed in attention is all you need.
So they have used only the position embedding.
Yeah, I didn't get it. Can you repeat the question?
I said that you will replace the positional embeddings from the transformer as an
No,
not
no,
as a
no.
complete transformer.
Yeah, yeah. Positional embedding are different in this paper. Like the main goal for the main role of the positional embedding was also different. Their main role was to accommodate the input and the output layer specifically, because we can permute the hidden layer but we cannot permute the input and the output layer. So they've used special positional embedding for that, and they've also used the hidden layer embedding, but that remains same for the whole layer, like just to just to make the architecture uniform. So yeah, I was there learning to optimize. It is a pretty important challenge. Like it is a very challenging task. So basically, they compared the result with the stochastic gradient descent and ADAM. These are the pretty popular optimizers. So let's quickly see the result first. So the this was an ADAM, and their the purple one, yeah, the NGGNN is this. So it is pretty good in the optimizing task. The graph is the training iteration versus the training loss, and they compared it with these architecture. So their optimizer is pretty good, and this one also. This one is the test accuracy and training iteration, and we can see this is the Adam optimizer, and the purple one, the NGGNN. Their NGT transformer is the second best after the NGGNN. We can see that in this also. Yeah, so basically,
So I have learned that the GNN using STD, not Adam.
yeah, the NGGNN and are you asking like are they using Adam optimizer to train that, right?
What kind of so they propose any new kind of novel
Yeah.
optimizing, or
No,
they have used only traditional STD?
no, they propose these optimizers. Matlab, they've used these proposed architecture for the optimizing task, and like
Got it. So what?
yeah, so Adam optimizer is basically for the to optimize. Basically, it has a momentum term and things like that to optimize to approach the convergence. But their approach can also learn this thing from the dataset. Like their dataset is also, yeah, the CIFR10. Basically, in this dataset, I can explain you like it has features like, for example, weights, bias, and then corresponding output. So basically, the thing is we should optimize the weight such that this output is pretty accurate or accuracy is high. So they've trained on that data set and then performed the optimization task and compared it with Adam. Yeah, I didn't get it. Your voice is cracking.
So just said that I've got it.
Okay. Yeah, so it was their setup is pretty simple. Like yeah, so each parameter ignoring the structure of, yeah, so there are two three things that they can account for. So basically, the whole thing start from here. Most of the, just a second. Yeah. So so basically, some optimizer or L2 task learning to optimize model based on the simple and efficient MLP, but with the stronger momentum terms. So their setup to compare is pretty simple. They have a feed forward neural network, and then they have some variant feed forward. Generally, how other research have optimized, like the task is to use a similar thing as an Adam optimizer. The other paper uses the feed forward neural networks. Then some uses feed forward plus LSTM or just the LSTM. So they have compared with three things like FF feed forward, then LSTM, FF they have also compared, then feed forward plus NFN. NFN here is the another architecture. The proposed this FF with NFN. It is proposed recently in Europe's 2023 paper. So they've compared it with that also, and their are better. So it is just the experimental setup like this I have described. So related work and then conclusion. The limitation is two main limitation are mentioned. The first one is that they cannot account for the transformer, and the second one is that it is only for the 2D image or 2D datasets. These are the two limitation, and then we have appendix section like expressivity of the GNN. Like this is the main reason, like what kind of symmetries they've used and how they have like they compare the positional embeddings, as well as they have described this MLP as a graph, and which I've already explained. Like this is their weight matrix, this is their edge matrix, and then yeah, this diagram I've explained like how the kernel they've used as a feature, then flattening layer, yeah, and then the normalization as a graph. So transformer as a graph they've explained a little bit, like the q queries and value pairs, q keys and value pairs. So it is from the not from the standard transformer, and these are there some experimental details of the dataset. The probe feature, yeah, there's just one line. We use the probe feature in the INR classification, and they've compared. So basically, probe feature using probe feature is a good deal. They've attained the better result, and yeah. So this is their detail, like on what k values they've tested, on what activation function they've tested. Like they've considered these activation function in each layer, like any one of these. Then skip connections, yeah, and this is their setup. These are the results mostly. Yeah, so that's it.